It has a normal and a tangential components. So where do we use this? Well, sometimes motion follows along a curved path, and you can describe the motion using a variable. Let's call it s. Okay, it's this s is not necessarily along the x and y axis, but it's along a curve. And I'll give you the curve, or you might have to find the curve. So this s is called a path coordinates. So for rectangular coordinates, we had the I, j, and k. For path coordinates, we have a different set of unit vectors. Okay, I'll call this as ut. U signifies that this is a unit vector, and the t signifies that it is a component which is tangential to the motion along that path. So when you have a curve, you can always draw tangent to that curve, and that basically signifies the tangential direction. The other direction is normal to the tangential direction, okay, and it's called the normal component. And these two vectors, ut and un, are unit vectors, just like I, j, and k are unit vectors along x, y, and z. So now associated with any point is a radius of curvature. Okay, so this is you can draw an instantaneous circle, right, with radius rho. And clearly, since the path is not a circle, it's some random curve, the radius of curvature rho will keep changing with time. Now, if this particle was going along a circle, then clearly rho would be the radius of the circle, it would be constant. If S instead was uh, a flat plane, what would be the radius of curvature? What would rho be? It won't be zero. It'll be infinity. Okay, because the radius, because at any point of time the tangent coincides with the path coordinates. So if S is a circle, rho is r, which is the radius. If S is plane or a straight line, rho is at infinity. Ut is the tangential coordinate. I'll call it the tangential direction, and then un is the normal direction.
So is S a point, or is it like a section that's from?
No, so let's say the particle starts at O and it goes along along this curve. S describes the location of the particle at some time t. So it basically it's along the curve. So if, for example, if it was a circle, then this would be S. So it would be what? If this is theta, then S is what? R theta, right? That's just an example, but the curve may not be as nice as a circle. That is the path coordinate. Okay, so let's move on to velocity. Okay, the velocity is a vector. It is actually conveniently written as s dot ut. Okay, where s, assuming that s is given to you, in this case for the circle, for example, s is r theta, then you can find velocity by taking the first derivative of s and then multiplying it with ut. I'll write that as v times ut, where v is the magnitude of the velocity. So you can see that it's very convenient to describe the motion of the particle, that is, find the velocity, because it just depends on the tangential direction. In case of rectangular coordinate, you have to write as a function of x and y. Question?
Just, I forgot, but can you find that in terms of magnitude, but you actually do that term? So we deal with the magnitude of this, so like,
Oh, you want me to write?
you find the magnitude.
So this is, by the way, ut is a unit vector, and then v is the magnitude, or s is s dot or v is the magnitude. So the velocity or any vector can be written as the magnitude times the unit vector, and this is exactly the representation. So unit vector ut times the magnitude. Yes, the magnitude is the speed, because we are interested in finding the velocity. So in order to find the acceleration, you will have to take the velocity and differentiate with respect to time. Okay, and there is a derivation in the book. What happens is that ut actually is a function of time. You take the derivative of a unit vector and then use that information to find the acceleration. So you want to look at the book. I'm just going to write the final answer. Comes out to be at ut plus an un, where at and an is the magnitude of the acceleration in the tangential and normal direction. So it turns out that you can derive that at is simply the second derivative of s, and an is s dot square divided by the radius of curvature at that point. So I'm going to rewrite this in this fashion: s double dot, or I'm going to write this as v dot, because we wrote the magnitude of velocity as a v, plus v square divided by rho un. Okay. Okay, so you could also, uh, so another thing you want to remember is that, remember we did a formula v dv is a ds, section 12.2, I think. It turns out that you can apply this formula in the in this particular coordinate frame, except that you'll have to replace a with at ds. So this way, if you're given at, you can then find the velocity using that formula as a function of s. Okay, the final thing I want to tell you is that remember the acceleration formula has a rho in it. which is the radius of curvature. How do you find the radius of curvature? So what you'll get in problems is you'll be given a curve y equals f of x, and from that curve, so you have to find rho. So an example of a curve would be the parabola y equals x squared. So if you want to find rho from the curve y equals f of x, then the formula for rho is this: 1 plus dy dx square, the whole thing cube, and the square root d square y dx square. Okay, so you do not have to remember this formula because the formula sheet has this formula. Okay, this thing here is the magnitude. So whatever is here is going to only give me the magnitude, not the sign. So for example, if I want to find the magnitude of -1, that's 1. The magnitude of 5 is 5. Okay, it basically takes the negative sign out of the equation. Okay, or if you have negative 0.5, it's going to be simply 0.5. Yeah, that's the absolute value. It gives you the magnitude. Absolute value. Okay, is that clear? Okay. Yeah.
I have a question. So for the v equals at ds, is it the tangential velocity?
Yes. No, tangential. No, v is the velocity, the absolute velocity, but the magnitude, and at is the tangential component. The way you get this formula is actually from this. At is v dot, and you can use that to find s. At is v dot, which is v dv ds. Comes from here. Yeah, the derivation is in the book. If you think this is confusing, they have derived this equation. Okay, so let's solve some problems. Okay, an automobile is traveling on a curve having a radius of 800 feet. So what we're given is rho is 800 feet. If the acceleration of the automobile is 5 feet per second, so when it says the acceleration is 5 feet per second, it means that you're given the absolute value of acceleration or the magnitude of acceleration. Find the constant speed at which the automobile is traveling. Okay, so you've been told that the automobile is traveling at constant speed. So when you're told that, it means that the rate of change of velocity is 0. This means that the speed is constant. So we need to find the velocity, right? But the rate of change of velocity is 0. That's what is given. So since we are told what the acceleration is, let me try to write the formula for acceleration in the tangential and normal coordinates. So a is at ut plus an un. At is v dot ut plus an is v square divided by rho un. Right? I'm given that v dot is 0, so that goes away. So acceleration is simply v squared divided by rho times un. Now I am given the absolute value of acceleration, so absolute value is simply v squared divided by rho. So this is equal to 5, but v square is, well, v is unknown, so we write this as v square divided by rho, which is 800, equals 5. So v square equals 800 times 5, which is 40,000. It's 4,000. And v is square root of 4,000, which is 63.24 feet per second. What's that?
When you say v dot dt plus v square over rho,
Yeah.
where's another thing in?
Yeah.
Where's divided for delta?
There's nothing divided. It's just, it's v square. This is the magnitude. This is the unit vector. There's nothing divided. Sorry, I wrote it. Yeah, so
So it has no value?
so acceleration is a vector, and a vector always needs to have a magnitude and direction. This thing is the magnitude, and this thing is the direction.
Okay.
If I need to find the magnitude, I just take the first part. I don't need the direction because I'm only given the magnitude. Yeah, so if you go back to the notes, you want to always think of this figure. This is a unit vector in the tangential direction, and the normal un is the normal direction. Okay, any other questions? So an automobile has a speed of 80 feet per second. So again, when you're given the speed, it means you're given v, it's 80 at a point A, and an acceleration of magnitude 10. So the magnitude of A is 10, acting in the direction shown. So you can see the acceleration is in the direction which is 30 degrees to what I would call the tangential direction. So the first question is find the radius of curvature of point A and find the tangential component of acceleration. Okay, I would try to write the formula for acceleration first because I'm given that. So A is v dot, let me write this as ATUT plus ANUN, which is v dot ut plus v square divided by rho times un. Okay, so I got to find what rho is. That's an unknown. This v dot is actually at, right? V dot is at, as you can see from the previous formula, and that is an unknown. Okay, v is known, So I know what the magnitude is. I know the magnitude, and I know what v dot is. I know this. I can try to write the magnitude of A if that is much easier. So I'm going to erase this and write the magnitude of A. It's v dot square plus v square divided by rho square. Okay, so again I know v. I do not know rho. I do not know v dot, but I know A. Okay, so this equation here has two unknowns, right? The unknowns are rho and v dot, but there's a single equation. Okay, I cannot solve for two unknowns with one equation. I need some more information in order to solve for those two unknowns.
Are you getting the square root from? Up from the magnitude?
Yeah, the magnitude is, this came from the magnitude. The magnitude is x squared plus y squared the whole square root. Okay, so the question is how will I solve for these two unknowns if I have only one equation? Yeah, I can solve for one of them, but I cannot solve for one of them because it's one equation, two unknowns. What does algebra tell you? You need two equations to solve for two unknowns, right? I can't solve for two unknowns with one equation. So I've used the information of, well, I've used A, where I will put that value. I've used V, AD. So it looks like I've used all information. Have I used all the information? So look at the figure. I've not used the information that the angle made by the acceleration is 30 degrees. It's not showing up there, so I need to use that information. Okay, so the way I can use this information is if I know A, right, then I can find if I know the magnitude of A, and if I know the direction which the magnitude makes with the normal tangential direction, then I can find the tangential component. AT is A times cosine of 30 degrees. So A is 10, cosine of 30 is 0.866. So it's 8.66 feet per second. But what is AT? AT is simply V dot, right? Remember, see this? AT is V dot. So I've solved for AT. So this is part 2. The next thing I need to do is find the radius of curvature. I need to find rho. Okay. Now I could use that formula. I know V dot. I could use this equation, right? Now, because I know the value of V dot, it's 8.66. I know magnitude of A. I know V squared. I do not know rho. I could use that, but I think there's a simpler way of finding rho. You don't have to use square root. Since we know A and we know the direction made by A with the tangential direction, we also know the normal component. AN is simply A times sine of 30. In other words, what this is telling me is it's giving me this component. But A sine 30, this is AN, is V square divided by rho. Okay, so A is 10, sine 30 is 0.5, V square is 80 square, rho is an unknown. So if you solve this, you get rho equals 1280 feet. This is part 1. Okay, so this is another way of solving it. I just use this way because uh, as opposed to this one where I have to take the square and take the square root, here I sort of escape taking the squares and square root. It's simpler. It's simpler to compute, but both of those formulas will give you the same answer. If you try the first one, you should end up with the same answer. Okay, any questions on this? Yeah.
I don't know, but I'm sorry, but you know how you said the radius equation for rho is like 1 plus y prime squared?
Mm-hmm.
We treated it as like v dot.
No, that's no. So you cannot. No, I'll tell you why. Because in that formula, it's basically only a function of, so the dy dx is a function of y and x, but the v dot is a function of v and t. There is no time in that. The rho formula has no time in it, so do not make the mistake of. So in this formula, there is no time. That is, there's no dy dt or dx dt. Do not use it. That's incorrect. It's only a function of the curve. So that function is only a function of the curve. That doesn't depend on time. Actually, I think I have a problem where I do. Yeah, I have a problem where I talk about how to use that formula. This is the question. A box is sliding along a curved path defined by the parabola y equals 0.4x square when it is at A with coordinates xa and ya is given. So this is xa, right? This is ya. The speed is 8 meters per second and increase in speed is 4. Let me write that down. So v is 8, v dot is 4. You got to find the magnitude of the acceleration of the box. So what I would do is I would write the formula for a first and then find the magnitude. So solution. So a is v dot a no v dot u t plus v square divided by rho un. So if I want to find the magnitude, I need to take the square root of v dot square plus v square divided by rho square. So in this formula, this is an unknown. V dot is given to me. V is also given to me, right? V dot and V is given, and the rho is an unknown. Okay. However, you can find rho because you know a formula for the curve. Okay. Rho is 1 plus dy dx square, the whole thing raised to 3 divided by 2 t square y dx square. Okay, so y is 0.4x square. How did I get that? I got it from this formula. That's the curve. I need to find the radius of curvature. So what I'm trying to do is I'm trying to find rho. Okay. So dy dx is 0.8x and d square y dx square equals 0.8. Now in this case I want to find dy by dx at a specific point. The point is x equals 2, y equals 1.6. So what I can do is I can find dy dx at x equals 2. So that gives me, so I need to put x equals 2, I get 1.6, and then d square y dx square at x equals 2. It doesn't depend on the values, right? So it's just 0.8. So now if I put these values in here, I need to put dy dx and d square y dx square over there. I get, so you're going to check me on this. I get 8.39 meters. Okay, so now I know what rho is, so I can find A. A is square root 8 square plus, sorry, it's 4 square. V dot is 4 plus 8 square divided by 8.39, the whole thing squared. So if you do this, if you compute this, you would get 8.61 meters per second square. Okay, so that's it. So there is a homework due this Sunday. Please do that homework. That homework, homework 1, and the prereqs are going to be on the first exam. The first exam is exactly a week from today. It's at 5:30 next Friday.
So would the exam, would the questions for prereqs like be direct from there, or you just like included in this material?
You mean for the
For the prereqs, like.
yeah? So we have a handout. There's a handout.